Hello everyone, welcome to the next Hewlett Packard Labs podcast from Research to Reality. Today we're going to talk about quantum and quantum inspired. I have a great honor and pleasure to talk to two ladies, Aishwarya, Natarajan, hello Aishwarya,
Hi, Dejan.
and Grace Johnson. Hello.
Hey, Dejan.
These two ladies are our senior scientists in Hewlett Packard Labs. So quantum is pretty interesting topic, but can you introduce yourself and the area? How did you end up working on this area?
Sure. So I came to Hewlett Packard Labs around 2 years back, and now I started as a postdoc, and now I'm a research scientist here. During my PhD from Georgia Tech, I primarily focused on innovative techniques for computing, primarily physical computing, that more involved analog computing, neuromorphic computing. What techniques do we look at to get higher energy efficiency? How do we get fast computation? That's what I focused on then, and I'm continuing to work on that here.
Thank you. How about you, Grace?
I started at HP Labs about 7 or 8 months ago, and before that I was working on my PhD in quantum chemistry at Stanford, so I didn't come too far, still in the Bay Area. And there I was studying mainly how we use HPC to simulate quantum chemistry. But what I'm working on now here at Labs is sort of how would you think about using both HPC as well as future quantum computers to simulate applications like quantum chemistry.
So you touched a little bit on this, but can you tell me what are your roles and responsibilities in labs?
Yeah, so kind of the thesis of our small team is that for quantum computers to be useful in the future, they're really going to be integrated into HPC infrastructures. So you can kind of think of a quantum computer as an accelerator, but it's specialized for certain kinds of problems. So it's not kind of like a general purpose accelerator. So what I'm working on, in addition to some of my team members, is how you would integrate the quantum computer into HPC infrastructure, kind of both from a software and a hardware standpoint, as well as developing algorithms and kind of identifying applications where those computational resources would be most useful. So things like quantum chemistry, which is sort of my background, yeah.
Interesting. Aishwarya, how about you?
Yeah, so I'm in the AI research lab, part of the emerging accelerators team. We work on building the next generation of hardware accelerators, so more for general purpose applications. So what I primarily focus on is the silicon design of these rapidly searchable structures called CAMs, or content addressable memories, wherein you basically you input something, depending on the stored state, it returns the address back. So these are like highly energy efficient, really fast, and we tend to use these for a lot of applications ranging from, say, machine learning models for explainable and trustworthy AI to all the way to quantum-inspired problems such as for optimization and so on.
And how has your area evolved over the time?
So if I'm talking about, say, quantum computing as such, so we can we can go back all the way to the 1980s when Richard Feynman first struck this idea of quantum computing inspired by quantum mechanics. He basically brought this idea that, okay, at some point, quantum computers could outpace classical computing. And then that led to a lot of interest in the 1990s with Shor and Grover with their algorithms that could theoretically break encryption protocols and produce quadratic speedup. And then, recently we had the big players like IBM, Google, and so on claiming quantum supremacy. And now there is a lot of interest in quantum computing, not just quantum computing, but also quantum-inspired classical computing. Because I believe that these should work in concert with each other, because each of them has their advantages. So now it's being used in a wide range of applications, from drug discovery, cryptographic problems, optimization problems, and so on.
Nice. Anything to add, Grace?
Yeah, you definitely stole my answer. I had that whole spiel
That's
prepared
good.
as well.
That's
That's
good.
great. We can agree on that. I guess I can just add a piece. Kind of you mentioned quantum inspired and quantum. The idea, I think, that we're moving to sort of in the next coming in the last decade and in the upcoming decade is the kind of idea of having heterogeneous compute. So there are different modalities for quantum computing, superconducting, trapped ion, various things, and they have drawbacks. Like everybody's trying to improve them, but there's a high probability that certain processors are going to be, better for certain problems. So I think kind of where we're moving, you sort of talked about the history of quantum computing, but I think where we're moving as we develop these hardware is to sort of a heterogeneous ecosystem, right? I mentioned integrating into HPC as well, but you have this idea of having hybrid quantum classical algorithms and potentially heterogeneous quantum computers as well. So basically, for a given problem, a given application area, you would kind of design your resources requirements based on that algorithm.
So here's an opportunity to steal Aishwarya's answers. What applications are you working with?
Yeah, so like I said, my background is quantum chemistry, and I think that's the field of quantum simulation. So you mentioned Feynman. That was kind of the original idea of what a quantum computer would be used for, is to simulate quantum physics. So things like chemistry for drug design or materials science, solid state physics. In my opinion, these are the most promising applications for quantum computing. So those are some of the areas that we're exploring.
And TCAM have a little bit different applications, do they?
Yes, so it's more for optimization problems like like QUBO, like quadratic unconstrained, binary optimization problems, and you must have heard of the popular problems like traveling salesman, and say you need to book flights for or distribute games amongst different teams. How do you do that in a energy efficient manner? So the accelerators we are building, these arrays of CAMs, essentially could help you do that in a very fast, highly computationally efficient manner.
Very nice. And both your areas, when do you think they will start being used in a productized way?
Maybe you go first.
That's a good question.
Yeah, I think you.
I think
a little
it's
sooner for you, maybe.
Maybe, yeah. I mean, since we are still in the exploratory phase of the research, and for CAMs, we use these non-volatile devices called memristors. The labs has a very rich history in memristors. So even in terms of the chips we are building now, it's more like test chips and prototypes. It would be, I see this like a long, roadmap to go there. But at this point, even if it's, even if you're not commercializing it, we are still letting other collaborators use our hardware through the cloud system. Remotely log into the, say the DPE or the new chip we have to run your applications.
So they can be used today.
They can be used today.
But
yeah.
where do you see horizon of products? Is it 5 years, 10, 15, 50, 100?
Also, if it's for research purposes, sure, it's much less now, because it's very it's very rewarding as such to see other people use your hardware to map the algorithms. Because from my background during my PhD, we had these devices called field programmable analog arrays, wherein we would use it at workshops, at other universities, where even for education. So there, it was like immediate result, where someone would map their, say, neuromorphic brain-inspired application, and ta-da, you have your results. So.
And true quantum, when will it come to market?
I would say maybe I'm more on some of the conservative side, but I'm also not, I want to caveat and say I'm not a hardware expert, and we're not building quantum hardware. We're looking at integration of quantum hardware into HPC. But my sense is, at least 10 years out, if not more. I think what's interesting about this space is that it's kind of that idea that coming back to the heterogeneous part, like there needs to be significant, improvements in various aspects, right? All of the modalities and then all of the algorithms that sit on top of the hardware, right? The error correction schemes. And so there's just a tremendous amount of things that have to go right. And so, I would say maybe conservatively, 15 years, 20 years.
And given that distant future, how do you measure success from now until these 15 years?
Ooh, that's a good question. I think that the phase we're in now is sort of preparation and study. So we can think of problems as, characterized by whether you could have an advantage solving them with a quantum computer or not. And I think just looking through the lens of quantum chemistry, which I think I have, that's probably the best thing for me to stick to my lane. We have decades of work in that field of approximating the Schrödinger equation, and we do it really well for certain kinds of molecules, for certain kinds of chemistries. And there's sort of no point in using a quantum computer to do something that we can already do really well with a classical computer. But what we can do in the meantime, as we're waiting for quantum computers to improve, is to really identify the places in chemical space or whatever problem sets you have that could really be targeted by a quantum computer. So there's definitely a lot of, preparatory work in terms of identification of application areas, and then, as I said, improvements in algorithm design and error correction schemes.
Thank you. And Aishwarya, how do you measure success in your research?
So adding to what, similarly to what Grace said. So I think for me, when I think about success, there's you have your short-term goals and your long-term. So short-term is like all of us, day-to-day results. Oh yeah, my chip works, or I'm getting good experimental results. I'm, things are working according to my intuition. So, those small things are very gratifying for me personally. And looking at the big picture, the fact that the steps we are taking, the hardware we are building is going to contribute to something which might, change the world or, push the boundary of research. I think that itself gives me a lot of joy in terms of, what I do day in and day out.
Very nice. And of all these joys, what are you most proud of?
What am I most proud of? Since I've been here only for a couple of years, I would refer back to what I did during my grad school. So that was basically an intersection of the analog space and the neuromorphic space. So one of the projects in the neuromorphic space was trying to build bio-inspired neurons and synapses. So there is this very popular model called Hodgkin-Huxley neuron, where the scientists won the Nobel Prize in the 1950s for eliciting an action potential from a squid axon. So we studied and saw that the biological membrane has very similar properties to that of a transistor or a MOSFET. So we got inspired by that and built these fundamental models of neurons and synapses with analog devices. So that was one on the neuromorphic side. And another project which is very close to my heart is showing a programmable linear equation solver, basically trying to solve AX equal to B on reconfigurable analog hardware. So
very interesting.
Yeah.
Grace, what were you most proud of?
Yeah, that's a good question. I've also only been here, I guess even less time, 7 months, but maybe I can kind of connect two things. So I would say in my PhD, one of the things that I spent a lot of time on was figuring out how to efficiently use the available hardware we have today to simulate quantum chemistry. And so I was working on how to use GPUs and distributed supercomputing basically to simulate quantum chemistry. But this idea of efficiently using the resources we have, I think is super important. So I'm working on a project with some of my colleagues, including Masoud Mohseni, about how to, if we had several quantum chips, how would we efficiently use all of them? And that's a very non-trivial problem and potentially, bespoke to certain use cases. But that kind of idea of efficiently using the resources we have, like I did in my work during my PhD and this kind of project I've started now here at HP Labs, I think I'm really proud of that idea and concept because, wasting our resources is not a good idea. So.
Yeah, very
For
interesting.
sure,
Yeah. And you are developing different algorithms. Does open source in quantum and quantum inspired mean the same thing as when you open source your GPU program or CPU program or other programs?
Do you want to go first, Aishwarya?
Sure. I think in general, I believe open source is the way to go if you want more people to learn, more people to use, be it your hardware or software. So in quantum, there's this Quantum Open Source Foundation, which has open sourced a bunch of like quantum software for others to use. But since this problem has been there in, say, even like other fields like neuromorphic computing, where we all have our own hardware and our own like languages to compile, to map the application. So how do you have this, standard of common method of applying whatever algorithm you have to the hardware? That's like one of the big problems. And also with open source, since quantum hardware is not accessible to, say everyone, there are these quantum simulators which you can use. But at the end of the day, I'm not sure that the field is that mature for us to have a lot of open source science out there.
Yeah, I would say it's very young still, but I think it's super critical, especially as I've touched on a couple times. This idea of different hardware, quantum inspired or quantum being, or different quantum modalities being better suited to certain problems. So the idea that you need to have multiple options available and that kind of requires something like an open source ecosystem.
Does the same observation apply to standards?
Yeah, I guess it's similar to what we were saying in terms of how the field is not, that mature. How do we have this, universal standard amongst different devices or different software? And speaking of standards, even like questions like benchmarking, how do you compare this performance? That's also a very big question, right?
Yeah, I would say we're even still the quantum community is still sort of deciding on what are the correct benchmarks to use. Like we had that the supremacy experiment with the random circuits that people have used, but there are all sorts of issues with that. One of them being that it's not a particularly useful problem.
Yeah, everyone's debating about that. So.
Yeah. So yeah, that's still an open question for sure.
So you ladies do research, you publish, you go to conferences. How much do you benefit from these professional organizations like ACM and IEEE in our area or in chemistry? There are similar organizations. Who wants to take that question?
I haven't really been a part of any of those organizations, so.
Sure. I mean, since I'm from the field of circuits and systems, at least IEEE has been like super beneficial for me in terms of career development, going to conferences, meeting people at like different workshops. And also, I'm a part of the IEEE Solid State Circuit Society's Women in Circuits Committee. So it also, gives me a role in terms of contributing back because these societies were really useful during my PhD. So basically, the Women in Circuit Society runs these data-driven programs, looking at how do you increase female participation in STEM? How do you motivate underrepresented minorities to pursue research or pursue what they want to do, irrespective of what their background is. So yeah, has been very useful for my career.
Grace, what do you find most gratifying in your work and your career?
I think the ability and the freedom to learn lots of new things. I think that was the case in my PhD and has continued to be the case here at HP Labs. I have this kind of cool position where I just get to learn a lot and try to understand the field and make some informed decisions, and that's really awesome.
How about you, Aishwarya?
Yeah, learning new things, the flexibility of what I get to do, and the people. Yes, the team. I work with like really supportive, collaborative team, and it's such a thought-provoking environment that it forces you to go out of your comfort zone now and then to explore new research ideas. And personally, I think I'm in a lucky time now, with hardware being really important, everyone's saying computers the new currency and so on, that I'm fortunate to be living in those times where I could try to contribute to that.
I can see that both of you are extremely happy with what you're doing. But just in case that someone give you opportunity to go all the way back, would you do everything the same way?
I guess, yeah, for me, at least since I'm in my early career, I think, yeah, I think I'd still follow this path of, pursuing a PhD in the field and continue, coming to work here, because I believe that, everything is a learning experience at the end of the day, because each experience shapes you one way or the other, right? So I try to not have any regrets, and, I hope to feel the same during my career in the future. So
Grace?
yeah.
Dan, I feel like this question was a bit targeted at somebody more advanced to their career, but yeah, I think I would at this point. I'm remembering back to when I decided to get a PhD, and I just thought quantum mechanics was way too interesting to stop learning about it. So I think I would have made the same decision again. I think maybe the one thing that maybe I struggle with a little bit is kind of connection to, I guess, community. Like as a scientist, you're pretty far removed from real world impact. I mean, of course, you could have a huge real world impact, but my growing up, a lot of my family were doctors, and I kind of saw that as like they really, every day they knew what kind of good they were doing in the community. And I think that's maybe one thing that I struggle with a little now is making that connection to, how is my work impacting communities for the better. So I haven't quite reconciled that. I'm not sure, if that would change, my career
you work
trajectory
in quantum
now.
chemistry, so I'm sure that's going to be
Right, maybe.
relevant.
Right, but
So ladies, you don't believe if you come up with all these amazing algorithms that you won't solve all the world's problems and have much broader good than what your
sure. I mean,
parents solved.
I think that's what you tell yourself, and I think it is true in a lot of cases. But there's something that's really satisfying about meeting face to face with people who you're impacting. So I don't know. I haven't reconciled it yet, but
I think it's more like you get the immediate gratification,
Yeah,
right? As
right.
you're in the medical profession,
Right.
But I guess what
maybe when we're like 90 years old,
maybe
yeah, we'll have that gratification. Yeah.
And a lot of what we're doing is like looking into the far future. So I hope what we're doing is helping the broader good. At least when it comes to say hardware accelerators, which we are working on, it falls under this broad umbrella of trustworthy, unexplainable AI, and that has a lot of applications, right? Like say in like clinical practice or healthcare, you need to know why this model spit out this result, like why is this happening? So that way, maybe it's my naive way of thinking, but in that way, I believe that having this, you map the model to the silicon to this hardware, and if you know why this is happening, that does help the community at the end of the day. Maybe not now, but far into the future.
Our audience likes to know a little bit more about you as people, persons. And so one of the questions they're asking is whether you read any good book. Mm-hmm. Can you recommend anything?
Well, I do like to read a lot, read mostly fiction. So I do like philosophical fiction, like magical realism kind of books. One very interesting book I read recently was this book called Midnight Library. So it's basically about the choices you're given in life.
Oh,
and
I've heard about this.
Yeah,
I heard it's really good.
Yeah, having an existential crisis.
Yeah,
and
yeah.
It's supposed to be, I don't know, it's supposed to be a good book, and I really liked it. So,
Okay.
and another author I would recommend is Haruki Murakami. Like, I like his, magical realism kind of books. So, takes you to a utopian world.
Grace?
Awesome. I'll do a fiction and nonfiction. So I recently read the first book of the Wheel of Time series. I think there are 14 books or something, so
Oh, wow.
I've got a
That's
lot
a
of
lot.
time to fill. But yeah, that was pretty good. I used to read a lot of fantasy when I was younger, but I did not have a ton of free time in my PhD. But I have a little more now, so that's great. And then I also read a really wonderful memoir called West with the Night by Beryl Markham. She was a pilot in the beginning of the 20th century, and she was the first person to fly from Europe to North America in a really small plane. But her writing is just beautiful and incredible. So I would totally recommend that if you just like to read beautiful writing.
So you said that you have a little bit more time. So what do you do in that spare time?
Read more
Yes.
fantasy, I guess. I grew up in Salt Lake City, Utah, so I kind of grew up, in the mountains and the desert. So I'm definitely happiest when I'm outside, backpacking, biking, camping, skiing. So.
You, Aishwarya?
Yeah, similar. I love being outdoors. I love the nature. And, I moved from Atlanta, Georgia to the Bay Area. So yeah, the easy access to the mountains, hiking, backpacking around the Eastern Sierras. So having access to these beautiful mountains, waterfalls, that's what I do. Otherwise, yeah.
So the last question I have is, how is life different in India, Atlanta, and here?
Yeah, like I grew up in a coastal town surrounded by beaches and, of
Which
course,
one?
In Kerala. It's in the south of India. And I was very lucky to have a very supportive family who are also in scientific or medical profession. And my family is back in India. And then, I moved to the US for my grad school. And again, found a wonderful group of, friends in Atlanta and, continuing to enjoy that life in the Bay Area.
And Grace, how about you?
Yeah, I think what I've loved about the Bay Area is that the access to nature is something that I shared with what it was like growing up in Salt Lake. So that's really felt like home. I think what's quite different is that there's definitely like a hustle in the Bay Area, which is, you learn a lot, right? It's really, really cool, but it can sometimes be a bit exhausting, having been here now for 7 years. So I think that's quite different from Salt Lake. Salt Lake is more, maybe more about other things. Yeah.
The slot canyons.
Yeah, the slot canyons. Yeah, going canyoneering or touring on the weekends or whatever.
Ladies, great talking to you, learning a lot about quantum,
Thank you.
quantum
Yeah.
inspired, and many
Thank
other
you, Dan.
things.